But then again, hello and welcome everybody. Thanks for being here. Thanks for your efforts towards the challenge. And today we will be presenting your results, or you will be presenting your results, I must say. So just shortly to cover what we have been doing, we have been analyzing data such that we can use the vehicles of DPD in the future to make all cities more livable, right? There are a few different directions that we explored there, and we ended up doing 2 of those. So today we will start with this short introduction of mine and also of Joni and Janne. Afterwards, we're going into the 2 teams that ended up identifying areas with high and low vegetation in the cities. So the problem we just discussed with the cities heating up and making them more green, but also the mapping of accessibility of public transport, which is of course also a super relevant topic. So without further ado, I'll first ask Janne to just give some brief words from DPD's side.
Yeah, I think I already saw everyone and had separate meetings with them as well, but really curious what the outcomes will be. Maybe good to know it's an important topic internally, also within DPD Group, to really start exploring those initiatives also for greener cities. So it's a hot topic. We're experimenting with a lot of different sensors to reach our goal. So really curious what you guys are bringing to the table today.
Very nice. And then, of course, besides DPD, we also collaborated on yachts for this, where Joni is. So,
yeah. So, Jess, I think I in the kickoff meeting also said that we are a university, very young university, 6 years old, and the unique part is that we focus on data science and entrepreneurship. That's the masters especially. And my role within JETS is that I am responsible for the startup incubator. And one of the reasons to join this challenge is that I'm hoping that maybe one of you guys are so enthusiastic that you guys want to continue with this. And if you do, if you want to continue and think that you can make a startup out of it, then I'm really happy to talk to you and to see how we can help you in all ways possible. Yeah. So please do reach out if you think about a startup, if you want to continue this, or if you have any other ideas, that's possible as well.
Very cool to get such an opportunity, and the same holds also on DPD side. I heard that they're also happy to support. So please reach out if that's the case. Well, then, as mentioned, we are going to the challenges have been using, amongst others, computer vision to reach their goals. But I'll just stop my whining and give the floor to the people that did the hard work. So, without further ado, with the first team start their presentation.
Okay, welcome to our presentation about urban green vegetation. We are really enthusiastic to show you what we have done and what the results are for that. So first we will talk about the goal of the project, then we will talk about the data and the models we have explored, green vegetation density calculation metrics. So what are the findings there and how did we do it? And then we have the results and analysis based on that calculations. And then finally, we have the conclusions. So what did we do right now? What is the conclusion about our results? But as well, what can be done later on. So first, the goal of our project about green vegetation. We want to create with video streams of the city, determine if an area or location needs more green density than others. So, for example, in some parts in the city, you can see that they need more efforts to increase the green density than other ones. And how do we want to do that? We want to do that with exploring the suitable street view style video data sets and try to train them with computer vision models. Furthermore, we want to train the computer vision models to extract the green vegetation classes in the scene. So if we are able to extract that, then we can be more efficient and more effective to locate where there needs more effort for the green vegetation. And we did as well determine the metrics to define these greenery levels in the scene. Then the models. We have explored several fully supervised models. The first one is a two-stage approach consisting of a CNN-based model integrated with the mask R CNN, which is simulating panoptic segmentation. For example, the mobile net plus mark R CNN and the efficient net BO and mask R CNN. Another one that we have explored is the future period network, the FPN, based on panoptic segmentation approach, with, for example, the efficient PS, the Dectron2, and the UPS net. And the last one is we as well look to attention network-based model, such as SegFromer. So the metrics to quantify the green vegetation density in multiple aspects, we use different indicators. Were used. The one that was really as well aware in the articles that we have read, the academic articles, was the normalized difference vegetation index. Other ones that we have used is the green view index and the vegetation structural diversity. So I give the word to the next person.
Okay, thank you, Yari. So basically, we were looking into exploring how we could measure green density, or basically, since the modality that we have been using is digital images, and to be more specific, videos, basically we are trying to calculate how many pixels represent green vegetation. And one of the approaches that we were also looking into was a multimodal approach using satellite data as well. And the most suitable metric or kind of sought after approach for measuring green density or green vegetation in satellite data is what is called as NTVI, which is similar to calculating number of pixels in images, which is the difference is this is a bit more normalized and can be extended for infrared images as well. So that's one of the metric that we used. And the next one is called as GVI. And as you can see from the formula, it's pretty straightforward. We calculate VI, which is the vegetation pixels, for example, trees, and T, or we can keep increasing that particular variable depending on the number of classes of vegetation we have in the scene. And since we had up to two of the vegetations that were labeled, we went with VI and TI, VI being representing vegetation such as trees, etc., and T representing other vegetation, and in our case, which was just the grasses on the ground. And it is divided by the whole the total number of pixels, and this gives the value of the green density. And this is how it is calculated using GVI. And the next one that we used was a bit more, I should say, intuitive, making use of Shannon-Vernier index. So where we use multiple vegetation, CI representing the values of vegetation out the vegetation types we are calculating, and the overall pixel count that we are measuring. Similar to the previous one, except that it uses an index which is kind of predefined by the formulas or the kind of lookup table that was defined by Shannon and Vernier. So again, these are some of the tried and tested metrics, and we found especially the second and the third one were more suitable for street view data sets that we were using, and hence we went with these metrics to calculate green density in a given scene. So next would be the first model that we built and that worked, and Claudia will be explaining it here on.
Thank you, Bruhan. So the first model that we explored was mobile night using mask RCNN for the panoptic segmentation. And to try out that the metrics that Bruhan just explained, what we did was to select just a city from the cityscapes data set. That data set contains cities from all over Europe. We just choose one, in this case, Munich. And we did different like testing with those metrics. So the particularity about the cityscapes dataset is that have only 2 labels for nature. One is labeled for vegetations that takes into account the trees, and the other label is terrain that takes into account the ground surface, terrain surface, such as grass. So it is important to notice that this will affect how our formulas are applied, and hence the results. So I explain a little bit about that. Next slide, please. Okay, so for example, in this case, we have like in the image on the left is the original image applying the MobileNet plus mask RCNN gives us the panoptic segmentation. And in this case, the GVI index, as Burhan explained, is just taking into account the number of pixels that contains any type of vegetation in the image. This would be the trees and the grass, and divided by the total number of pixels. And on the opposite side, the BSD, it takes into account the different types of vegetation that there are in the images. So in this case, we have 2 types of vegetations that are the trees and the terrain, and then that's how it's calculated. So that's what I was saying, that it depends a lot on your label data set. That is important to calculate the diversity. That is the diversity of your vegetation. That is what BSD is calculated. Next slide. So this is like the same. So for example, if you can see in one image, we have the original image, and the other one we have just to calculate the type, the amount of vegetation that is in the image, that is case GVI, that is very low, but also we can see that the diversity of vegetation is also very low, because as you can see, there's only one type of vegetation in the image. So the next one. So this is like similar to the first one. I just wanted to make things clear that, as you can see, it's just going to calculate median level of GVI, just because there's enough like trees and terrain in the image, but also a medium level of BSD, because also there are 2 types of vegetations in the image. So just to make clear, one makes like the amount of vegetation in general in the image, but the other gives you also the diversity and is dependent on your label data. So in this case, you can use it different ways. You can calculate the overall metrics for the whole data set, in the case the whole city that you have, but you can also calculate for different part of the city. For example, if you have you want to calculate for a certain like street, then you can take the amount of data, the amount of images or video data for that street, and just make the calculations of GVI or VSD per street. So this is important to know that it's like average by the amount of images of the street. So that makes you like a more reliable score if you're having like different number of images per street. And this is Had, I think it's gonna explain. Mm-hmm.
Yeah. So for now, like as you can see, we already present like the first model that we used. And one of the things that we came up with is that like to see whether this evaluation metric, the GVI and VSD, will be robust among like other CDs data set. So that's why we tried this second model called Detection 2, which is like quite like popular model among the panoptic segmentation problems. And we use like one of the models pre-trained in the COCO data set using the pre-trained panoptic FPN model. The reason why we don't have the custom data set, I will explain that later as one of the limitations. But that is like the main thing is we are using the Detection 2 model in order to output the panoptic segmentation and to see if these 2 evaluation metrics mentioned above is also robust among not just one city, but like, let's say a random city, a random images that we have panoptic segment. So if you can go on the next slide. Yeah, so in here, we try to use this pre-trained COCO dataset model in order to predict the panoptic segment on the BDD 100K dataset, the test one. And the output we have is about like 10K images. And then we calculate the overall GVI and VSD of these images. And as you can see that because these two evaluation metrics have like 2 different approach. So you can see that it's like a way different number in here in overall. And it's also because of how we treat the labels of vegetation in this cocoa data set. Because like in cocoa, the label are for vegetation are only like flower, tree, grass, and sidewalks and ground. Why we consider sidewalk and ground is because we also think that like they have a possibility to grow plants in there as well. So that's why we count it towards this metric. And in the end, after like including all of these, we have these two overall GPI and PSD. And the conclusion was these two metric is also applied not just only in a certain city, but it can be also be applied in like a random images, a random like segment of the video, for example. So it's like a very robust metrics in counting vegetation. But there are also like limitation on these model, which is first, we couldn't able to use the BDD 100K train data set, the custom one, because we don't have access to like a way good GPU for that. And also the model is really lack of like hyperparameter tuning as well. So those are like two limitations that might affect this result that I present. And if you can go on this next slide, you can see that in here, the model, the pre-trained model is also output like a really nice result, because like in the first image in here is one of the image from a video in the night. And you can see that it still can detect like what is the tree in here. And the tree in here is not even having the leaves, like just only the tree on the winter, and it still can detect it. And then the second one is like during the day is, yeah, the normal tree. It can also be detected as well. So I would say this model of Detectron 2 is really robust on doing this panoptic segment task. And also it means that our metrics is also robust because this can be applied in like random city. Yeah, so that is from my side. And then Animesh, I believe, prevent the next model.
So, so next, it's also important to see what didn't work and why it didn't work. So the other two models we explored were efficient PS and segformer. So one of the approach we took was testing these through GPUs on our system. So not a GPU that can train BDD 100K on Detectron, but a very low end level GPU. So what we found was, first thing is that they ran into a lot of compiler issues on system. So one thing that might come to your mind is what about real-time inferences. So about these models, these aren't suitable for real-time inferences, and they don't infer with the CPUs only. So that is one of the drawbacks, and they would run into a lot of compiler issues as well. I mean, they could be debugged, but that will take also a lot of time. So this us exploring this also involved weeks of debugging, but still they either have dependency issues or they have compatibility issues. So that is why these for this challenge, these two models didn't work even on GPU inference. So that is an update on the other two models, and because it's also important to know why other things didn't work.
Okay.
Yeah.
Thank you, Animesh. So that brings to the conclusion part of our presentation. So basically, what we did so far was try different models which were suitable for this project. And we initially looked into what was the best approach. And that the one that stood out was segmentation, and to be more specific, panoptic segmentation, which is a combination of both instance-based and semantic-based segmentation techniques. So a two-stage approach, what we trained initially worked, and also Detectron has worked as well to a certain extent, we can say, but it has got its own hurdles in terms of training the model, because it's a bit research intensive at the moment. And also would like to highlight, because we were trying to train these models to this project, to the requirements of this project on Google Colab, and which runs mostly on fairly old GPUs, and also the training time that is available is quite low. So the metrics that we identified were GVI, BSD, and NDVI. And after exploring quite a bit in the literature, we found these to be the most sought after metrics. And we took them as a good starting point and used them in the models that we trained for segmenting vegetations. And they have shown to deliver the kind of results that were expected. And so at this point, I can say that probably in terms of metrics, we can further explore what is available based on different vegetations as well. And also how, depending on the climate changes, and also the kind of cameras that could be used. For example, even for street view applications, one could use not just RGB, but as well as hyperspectral or wider spectral images. So which would be a much better representation of green health of the trees and green vegetation. So with that in mind, I would say probably depending on the type of the camera or the sensor that would be used, the metrics can be further explored as well. And the next slide would be, so what we have achieved so far and the current progress was in terms of using the metrics on the couple of models that we trained. And one thing that though we managed to achieve was using NDVI on satellite data, which was, to be honest, pretty straightforward because it was images and which was mostly clustering job. However, we weren't able to find a means to fuse both satellite imagery and street view data, and in turn create a much better, bigger cluster to say, or a region of interest to say where the data has, or the street view data has to be explored extensively. So that was one of the tasks that we couldn't accomplish, also, which was initially our objective of this project. And the last thing that I would like to point out is that at the moment there are much better panoptic segmentation models that are available. One of them, like Animesh pointed out, is efficient PS, and also Detectron 2, which has to be further explored. Because in this project, we directly used trained data that was available, and we tried to see how GVI and VSD is going to work. And the other one that is out there is Unified Panoptic Segmentation Network, which came out in 2021, I think. So these are some of the models that can be further explored and trained, and to see how it can be applied for the requirements of DPD in terms of assessing green density and green vegetation in an urban setting. So that brings to the end of our presentation, and thank you.
I think just adding to the last point, so as Ruan mentioned, also like training more efficient models, that also requires some infrastructure support. So all of this would depend on whether you are having that kind of infrastructure support, and if you're looking for real-time or post-video analysis for this. So yeah, that's one point I wanted to add. So yeah, that's it. That's it from my side.
Thank you. Thanks.
Thank you for your presentation. I think I wrote some questions down still, but it's really nice to see the collaboration on the presentation as well. And I hope that is in the team as well with receiving this, this detailed information, also training the models, etc. So that's really good to see.
Thank you.
Cool. Thanks, Jana. I was just talking to my computer.
I saw that.
But I was saying something similar as you did. Like, thanks, Al, for your presentation. Looked really nice. Explored different types of models. Not all of them worked out, but at least it's also a good body of research to see, like, okay, these different types you can explore. I've worked with Detectron 2 before, and that one was really successful. It's a bit older, I guess. It's like 3 years old or something. So, but would definitely be interesting to also see those results. But that is also something that DPD, of course, can explore further based on this research. Jana, you mentioned to have written down a few questions, so I say shoot.
Do you want me to ask them now, or I don't need an answer right away? But the first thing that I wrote down is, why did we choose this use case? What do you see as the added value for DPD? Brand, you already mentioned which sensors, which video material we should receive. We would really like some advice from you on that, so that we can explore that even further. I missed that a little bit in the presentation now, but if you can take the next step to really give us an advice on what we should explore for sensors and camera data, so we can use your knowledge that you build right now and take it into account for us, so we can receive real-time data, or just keep in mind it's a moving vehicle. It's different than satellite. So I really would like to get some more advice on that. Just one question I saw in one of the images, there was like a green car and it also counted for vegetation. So I was just really wondering, how does it determine if it's really vegetation or if it's just a green color? But that's just a question from my end. Let's see.
I think I can answer that question right away. Okay. So with segmentation, panoptic segmentation or object segmentation, what we are doing is we are selecting the pixel color. So if we see that, okay, it is quite close match with some of the car colors that are being used with the companies. So we can shift that RGB value so that it is quite distinctive to differentiate the green vegetation we are segmenting.
Is it just shade or also like shape of a tree in the machine learning, or the shape of a car?
Well, probably we could look that into as well, but yes, the shape matters as well, and that comes under object recognition itself. Okay. So once that's done, it won't be recognized as a vegetation, and also the training data would identify the car depending on the shape as it's a car rather than a tree. Yeah. So yeah, that way that should be taken care of. But yeah, that's a good question as well, and also that can be extended to other areas as well. What if the color of the tree changes as well? Yeah. As in, it's not necessary throughout the year it will be green. Yeah. So for that reason, we will have to explore like what other sensors are more suitable. And one of the limitations that I would like to point out as well was that the data set that we used, like Claudia mentioned, we looked into one city probably, and also you can see the time of the year is the same. So yeah. Sometime during April or just before autumn or something like that. Yeah. So gray clouds and the green is quite obvious. So if as time progresses during the year, the color of the trees changes, and we have to find a way to adapt to that as well. Yeah. So, and one of the solutions is changing or going with a much better sensor, which has a looks into much broader spectrum rather than just RGB.
Yeah. Yes. So that would be great if you could give us some advice on that one. But I agree. If it's now the same color and the same season, it's difficult to make a comparison, because ideally you would want to make a comparison between cities as well. Like that city. Greener.
Exactly. Yeah, because the infrastructure. Exactly.
Just one point I want to add more during our training model is that actually the detection model is quite robust on, for example, if the leaves of a tree is changing, will it detect it is a tree or not? Like it does, because like I try to using this model on not just like say images or videos on the day where it's like obvious that it is a tree, but it's also like at night, for example, and also if the tree doesn't have any leaves at all. So like when it's changing shape, and the model does predict out that it is a tree. It's just that the thing was like, because we don't have like object detection label to detect like number of trees on say a video, but more than like all the data set is available is the tree information is only available on panoptic segmentation. So that's why we went on to the task of, instead of object detection, we went into panoptic segmentation. But what I mean was this model, like there are models that are robust to all of these. But of course, like as Bruhan mentioned, if we does have a better sensor or like a better technology, then that would be also work, like to be further more better.
Already quite surprised that in the night you could just see the trees so well. I didn't expect that. So good to see. So I think to sum my questions up, it's more like, what's the business model for you guys behind it? And just an out of the box idea, I also thought like maybe it would be great to see bicycle paths as well. But that's just for the next steps. Right now we should focus on vegetation. Yeah, I think that's it from my end. I would just really kindly ask you to give some more advice on your end on what sensors would be suitable to really take the next steps for vegetation models.
So it would be great if you guys could add that to the final report.
Will do. as under scope of the scope of future work, and how what Hal was pointing out is probably another way to look at it is, say, if you're to kind of scale the data set itself by annotating vegetation during different time of the day and different time of the year. That's one of the workarounds as well with RGB cameras. So that could be done as well. So yeah.
Cool.
Yeah, really
Yeah.
good to hear. Yeah, cool.
Are
And
there,
thanks again for the presentation.
are there any more questions? Not as of now. Yeah,
Okay.
that's all from my side. Thanks for the presentations and all your efforts, of course, guys. But then we move on to the second team on the mapping of public transport accessibility. So please take the floor.
Our group looked at public transport, and we especially looked at estimated visualizing the crowd, how busy it would be in the roads, and see if we could say something about CO2 emission. So for today, some context, the steps that we taken and the hurdles and a few demos. We had a couple of talks with Jan of DPD to get some background requirements. Well, it was all on the start of this challenge. And we actually, one of the things we took from that talks was that it's for DPD by either, and correct me if I'm wrong, for data monetization. So what are possible other business models and green strategies for the main business. So we started with following the CRISP-DM model framework to structuralize our work. As I said, we did some brainstorming about what is it here, the problem understanding. What would be the relevance, what would be possible, would be contribution for greener cities, and what would be actually also feasible within the time frame that we had and resources and the available data sets. So we came up with a couple of use cases, and we just voted for which one would work according to the restrictions that we had set ourselves. So we came up with two. Both the crowdiness of traffic and the estimate CO2 emissions, or one metric of air quality. Well, this is a data set we all have used, so I don't think I really have to dive in this one again, right? So the model, we had two use cases for the CO2 estimated, and we made it in have light vehicles, cars, and trucks. We didn't consider lane detection. The crowd metrics was really cars, trucks, light, heavy vehicles, and pedestrians. For coverage metrics, actually the count of buses in certain areas. And traffic metrics were a combination of cars and trucks, so light vehicles and heavy vehicles. And for CO2, we weighted cars as 1 and trucks as 2, where they are emitting more CO2 than lighter vehicles. For preparation, we selected a couple of videos to test the concept. We focused on buses, trucks, cars, and pedestrians again. And this is actually, so what we did was testing a couple of models trained on the BDK 100. Well, the first on the RCNN was not so good in predicting buses. The Convenex was a bit better, and it was actually the YOLO version 5 that really gave better results. And then also tested YOLO V7 that was slightly better, but not that much. And I don't know, because I didn't see Sahil during the first half an hour. I don't know if he's in the call now, because he was going to add some more of the technical details.
I think I can take that up.
Yes, please.
So here we've selected two videos from the BDT 100K dataset, and the results that you see are from the YOLO V5 and YOLO V7 models for each video. So using YOLO V5 and YOLO V7, we are performing object detection, and as a post processing, after we get the detected objects like car, buses, trucks, and pedestrians, we are taking account of each of them, and the table here shows that. So these count will be further using it for maybe the visualization thing that Antoine maybe will show after this.
Yeah. Well, we first go to the hurdles. Was one of the for simplicity, we used available models and with no fine tuning. So when it was also with time and resource we had, the CO2 estimation is imprecise. For sure, we were struggling also. How could we really indicate? I mean, there are, when you make this footprint calculations, there are metrics to calculate those. But in the end, you can't be precise about which car is emitting how much, etc. So it's really a rough indication. Some team hurdles, which is obvious that I'm on page 100 of Data Science for Dummies. And so there was a lot of the technical work was, I think, with a few of us. So that, and there was summer holidays, so we were all out for a couple of weeks. So also we didn't do a couple of things. No time for comparison the model metrics and on the validation set. That's something, shame. And we use label data and validation set for visualization. So these are a couple of the hurdles. The good thing though is that we have a couple of demos. So use case 1 was the one with the crowd estimation. And I hope now that this one is going to work. Buses, pedestrian, cars, and trucks versus the date. And oh wow. Then also time of the day for buses. And there goes something. I don't know if this one really. So use case 2 was about the CO2 estimate. And this one is versus the weather. And we have one versus the, if it clicks through, versus date. In the year 2017. And I can't see you, so I don't know if you want to add something here as well.
So I'll just add up, to the visualizations we can see here. Basically, our main, main point of focus was to able to kind of, point out the most, point out the hotspots of the bus, of the heavy vehicle regions, so that we can kind of have like a small planning around that, right? So because some places of the city might have like a lot of heavy vehicle movement versus some place which should not have like a lot of heavy vehicle movement. So there was some points which we were actually playing around with that, and then hence we came up with a couple of visualization along with the use case on how we would technically approach it with, right? So these are the visualizations around with that. So I mean, the main focus of us here was to able to kind of point out how many heavy vehicles you can see at some particular area. But we did realize that from a vehicle's dash cam, that is technically not possible, right? We cannot really tell whether a particular vehicle coming from forward is a heavy vehicle or not, right? Unless we get like a higher level view of that particular area. So from that's where we came in, have a small conversation with DPD, and we got like a list of sensors which they are, they have been planning to integrate it into their upcoming solutions. That's when we came up with 360 cameras plus LiDAR integration to kind of have it as a future implementation scope, so that not just the vehicle which we can see through which we can see through the dashboard dash cam, but also the vehicles which we can actually map around with the 360 camera and the LiDAR sensor, so that we will have like a pretty general idea of what's around the vehicle, and then we can map it with the geo coordinates, so that the visualization and analysis might be more accurate in that scenario. So yeah.
Okay, thanks, Shiva. Now it should get to. So this was that from our side. Thank you. This is the team and the references. And if someone wants to check, we can also upload this in on the Slack channel.
Thanks a lot, Antoine. Very, very nice presentation indeed. Yeah, please upload all the materials in the drive, so that they are also usable for, well, also for reference from DPD side. And most, of course, thanks for your efforts and your team throughout these 10 weeks. Let's start with some questions. Does anyone have questions to ask here?
It was really nice to see. We had a lot of talks on it, on how we were perceiving things. So that was really nice. My only concern is still, like, we used a lot of static data right now, static videos. If it will be sufficient enough if we use like 360 cameras and LiDAR, can we really make this in position? Can we make this in place to create that added value? And I think it will be really relevant also for governmental organizations. So that's what I really like about this case. So we can really go to a governmental organization and discuss this with them. So that was really nice. But my main concern is that it's mostly based on static videos. And if we're exploring the sensors and maybe cameras for our fleet, will we get the same result? So that's a question that keeps popping into my head if I see your presentation. So if you maybe can take some advice for us or put a little note on how you perceive this, that would be great. Because I'm still struggling with that one.
Yeah, I would say that in this case, more data could lead to better results, right? It's a 360 view would at least be, you could also extract this type of data. So I don't think that you add on top of that.
Yeah.
Only the consideration is, of course, the sensors being a lot more expensive, especially the LiDARs. And also the amount of data that you will generate will need a very serious cloud storage. Because if you're driving with such a fleet, collecting point clouds throughout the whole day, then you will need a serious amount of storage.
Yeah, exactly. And then it would be maybe more sufficient if you just put a static camera that the government already has to use that instead of putting it on our fleet. So that's the thing I'm struggling with.
Yeah, I can imagine. Yeah, it would also be good indeed if the team in their final report can add some points on that.
Yeah.
Any other questions? Not as of now, no. Well, then Antoine must have told a very clear story if there are no questions. So that brings us to the end of this presentation, guys. First of all, from my side, I would love to thank you all for putting in the effort over these 10 weeks. I really appreciate it. Every time that we close up these challenges, I get a little fuzzy inside because people are spending their voluntary time to try to make the world a better place while teaching themselves and others around you. So I hope you really enjoyed the experience. I mostly hope that you learned a lot, and I also hope that DPD will be able to use your results in the real world, because in the end, at least that's the goal from FruitPunch's side. We're not only here to do fun projects, but the goal is to make some real impact in the real world. And that's why we really hope that all of these projects also end up in the real world to make the impact that we hope. So hopefully, like next year, there will be more trees here in Eindhoven, and it's less hot right now because I have really sweaty hands here behind my computer. So again, thank you, Al, but then I also leave it to Janne and Joni to give some final remarks on that.
Yeah, I think I already had a lot of questions. It would be great if you can incorporate that, but mostly I'm really happy with your presentations. I'm really happy that you took the time and effort to be part of this challenge. It really opens our eyes into what AI can do for us, and it will be great to take it to the next step. And I'm really happy if we can implement it as well. And I think that will be possible if we just take the next steps there. So really happy. It helps a lot with internally to really show what you can do to make it more visible. Also the little demos. That's just great. Also the images from the vegetation team. That's just something really feasible that we can show, and that makes AI a little bit more to grasp internally. So that's great. And thanks a lot for your effort, for your input, for the questions you emailed me, for the time we talked with each other to discuss use cases as well. It's really cool to see your point of view and compare that to the business point of view as well. So mostly, thank you.
Cool.
Yeah. Quickly from my side. First of all, congrats to all of you. I am not at all a data scientist and technical. I come from the commercial side of things, but I am so amazed to see what you guys done in 10 weeks with people that you didn't know at the beginning, and then do that remotely. I'm quite amazed. So well done.
Awesome.